So we're starting today with chapter 4. Now, we did a little piece of chapter 4 a couple of weeks ago. We talked about nomenclature. The majority of this chapter, however, is all about bonding and kind of how electrons come together to tie atoms together to make molecules. So our discussion today is going to start there. There are three primary ways by which atoms will use their electrons to form more sophisticated molecules or compounds. Now, two of them we're already familiar with, the ionic and the covalent. Ionic bonds come when we see metals and nonmetals coming together. We're talking about a transfer of electrons. We're concerned about things like charge balance and electrical neutrality and that kind of stuff. And that part was kind of evident when we did nomenclature. I needed a compound between magnesium and nitrogen. I knew that the magnesium had a positive 2 charge and the nitrogen had a negative 3. So to balance it all out, I needed 3 magnesiums and 2 nitrogens to give me magnesium nitride, Mg3N2. For covalent compounds, again, we've seen some of this in terms of nomenclature. We know that covalent compounds are made up of nonmetals. We know that those nonmetals share electrons. And because there are shared electrons, we don't have really any kind of hard and fast rule for how many of each kind can be in a given molecule. And so when we name them, we tend to just focus on how many of those elements are there and in what kind, what quantity. Metallic bonds are something we haven't talked about yet. We've talked about metallic properties, things like shininess, electrical conductivity, heat conductivity, malleability, ductility, that kind of stuff. But we really haven't talked about what makes a metal metallic in the first place, other than it's on the left-hand side of the periodic table. And it's really kind of interesting because what we're talking about there is we've got this idea that there are different kinds of electrons. There are core electrons and then there are valence electrons. We talked a little bit about valence electrons when we did electron configurations. The idea that the noble gas configuration gives us kind of those outer electrons and the inner electrons, the ones that are represented by the noble gas itself. Well, in metallic bonds, what we see is that those outer electrons don't actually belong to the atom itself. When a metallic sample forms, the collection of atoms take those outer electrons and they drop them into a pot in the middle. And those electrons are collectively shared by all of the atoms in the sample. Now, we call this phenomenon the sea of electrons. And it is that sea of electrons that ultimately binds a metal sample to other pieces of metal. And it's that sea of electrons that also explains why metals have the properties that they do. Because instead of having individual atoms that are sharing electrons or individual ions that are holding electrons, and bonding is a very personal kind of experience to that one atom, these atoms are collectively tied to each other. And so we've got thousands, if not millions, if not billions of atoms that are bonded together, tied together through this mutual sharing of electrons. And because they all have the same charges, they all have the same kind of general identity to them, there's a lot more flexibility in their properties as a result. And that's why we see flexibility, bendability, malleability in metals when we don't see it in other places. Because the bonding isn't a network of substances in ionic compounds. or in covalent compounds. It's very individual. So again, if we look at this kind of in terms of just a general summary, in ionic compounds, we see a transfer of electrons. The net result is that we got this array of positive and negative ions that are attracted to each other by their opposite charges. And even though it is a network in a sense, there is a lot of them that are around each other. All it takes is a little bit of manipulation, and instead of a staggering array of positive and negative, which stabilizes the crystal, you bump it just a little bit, and two of the negatives end up next to each other. Well, negatives repel, it's going to break apart. That's why salts are fragile. Covalent compounds, for the most part, we don't even get that much interaction with them. They don't interact with each other much at all. They're very, very individual. There are some covalent compounds that are capable of forming networks. They are kind of their own special category, and they have kind of unique properties when they do. I'm thinking in particular of things like carbon, graphite, and diamond. But it's much more common that you have a series of molecules that are loosely affiliated with each other. And for those reasons, they tend to be gases. They tend to be very low melting solids because there isn't a whole lot that's holding them together. Whereas in metals, we can see metals can hold together a very large array. And the difference between this array and the ionic array is all of those have the same charge. And well, you might think, well, wouldn't that mean they all repel each other? You have to remember that that sea of electrons is moving in between them and stabilizing them. So they aren't going to repel each other. That's why you've got to beat a metal sample practically to death to get it to actually break apart from itself. You have to beat it so that it is so thin that the brittleness of its depth is what ultimately breaks it. You can get it a foil up to 2 atoms wide. Tiny. Because that sea of electrons is going to stabilize it. It's going to keep it together. So we're not going to spend a whole lot of time talking about metallic bonding. That's a whole nother course, if you want to be honest. We'll come back to metallic bonding again in Chem 106 for those of you that are going that direction. You'll see it there when we talk more about solid phase chemistry. Let's switch our focus to ionic bonding here for the second. And take us back to chapter 3, where we talked about 2 important properties associated with atoms. Ionization energy, the energy it takes to yank out an electron, and electron affinity, which we didn't talk about explicitly, but is basically the opposite idea. Ionization energy was yanking an electron out. Electron affinity is putting one in. And usually when we put an electron in, especially in certain kinds of compounds where we are getting it closer to its octet, getting it closer to its noble gas configuration, we see a energy change for the better. Energy being released because the state with the extra electron is more stable than the state without the electron. So you think about chlorine. Chlorine has 7 valence electrons. It's 1 electron away from argon. Adding that last electron gets it to a noble gas configuration, gets it to its perfectly normal ion state. That's favorable. Its favorability is reflected in that negative 349 kilojoules of energy. That's how much energy is given out when that electron goes in. As opposed to sodium, which even though sodium is going to get a noble gas configuration when we take that electron away from it, we still have to get that electron out. We have to promote it to a high enough energy state that it leaves. So it's going to require energy, 496 kilojoules in particular. So from an electronic standpoint, over 400 kilojoules had to go in, only 350 came out. By that logic, the ionization process is one that would require energy. We would have to heat it and heat it and heat it to get it to react.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
Now hold on a second. We had to heat up the sodium initially, but once we moved it into that container of chlorine, we didn't have to heat it up anymore. Why? So take a couple of minutes. Why is it that even though the numbers for the ionization process would seem to indicate that we need to add energy to create sodium chloride, why is it that when we actually saw the sodium chloride getting created, it was giving off tons of energy, gave off a ton of heat, gave off a ton of light? We saw that in the chamber. Why? This answer here at the top, however, is actually really, really close to what we would think of as correct. What we were missing, the thing that we were not considering, is making the ions is not the only factor in making an ionic compound. Those ions have to attract each other. They're going to get bonded together. Simply transferring the electron does not create the bond. It just creates ions. So kind of like what we saw in the sea of electrons, those atoms were all bonded to each other by their mutual attraction to the sea of electrons. There is an attraction that exists between the positive ion and the negative ion in an ionic compound. Now we can quantify that electrostatic energy using this equation. You're not going to need to. Don't even bother writing down the equation. It's not that important. What is important, however, is understanding what the guts of the equation mean. So our electrostatic potential is really dependent on three factors. Two of those factors are the charges of the ions themselves. The larger the charge on the ion, the larger the charge on the ion, the more attracted they're going to be. So a positive 2 ion is going to have greater attraction than a positive 1. A negative 3 is going to have a greater attraction than a negative 2 because the charges themselves are bigger. And bigger charges are going to be more attractive. So that's the first factor. That's what the Q1 and the Q2 are all about. The other factor is the distance. Anyone that's ever played with magnets before knows all about this idea of distance. If I hold 2 magnets at arm's length apart from each other, they're not going to attract each other. But there is a certain distance that when I put them next to each other, even if I drop them and they weren't touching beforehand, they'll be touching by the time they hit the ground. That's attraction. And that's the similar kind of attraction to what ions are going to feel here. The closer we put them together, the more they're going to attract each other. So what this really gets into is size. We know that we're going to get those ions as close to each other as possible because that's the most efficient way to have it happen. But we're going to be limited in some respects based upon the size of the ions themselves. So here's where those periodic trends come into play. If I have an ion that is large, its ability to get other ions close to itself is going to be limited by its size. If I can't get anyone closer to me than where my fist is right now, it's going to limit how many people I can actually interact with in this space. Whereas if I have a smaller ion, I'm going to have a lot more attraction because there's going to be a lot less distance between my nucleus and the electrons of the other atom. So this is a direct callback to the end of chapter 3. Ionic size. Bigger is not better in this case. Bigger is going to mean less attractive. Smaller is going to mean more attractive. And we're going to find those substances that those smaller ions make are going to release way more energy when they form and take way more energy to break apart. And so we can quantify this with something called lattice energy. Lattice energy is the energy that is released when a crystal lattice forms, like what we saw in the video. So when we go from raw materials to ionic compound, lattice energy represents the amount of energy that is released in that process. And if we look at the actual values of the ionization energy, we will see that there is a relational component to this. So take, for example, all of these. All of these compounds feature an alkali metal and a +1 charge, and a halogen with its -1 charge. So all of the charges in that top section are all the same. What's causing the variability in ionization energy? Size. If I compare these first two, I'm really comparing, because lithium is the same, I'm comparing the fluoride ion to the chloride ion. If I look at the periodic table, I can see that the chlorine is going to be bigger because it's got more energy levels. That bigger size is going to give me a less attractive ion. Lattice energy drops by nearly 200 kilojoules because of that extra energy level and that inability to get those ions as close as possible. It cuts both directions. Let's take a look and compare two chlorides here. The sodium chloride versus the potassium chloride. Same thing though, right? Sodium and potassium, both alkali metals. Potassium has an extra energy level. It's a little bit bigger. We see a drop in ionization lattice energy as a result. But when I compare, so let's just do a quick comparison here. Magnesium chloride versus sodium chloride. Big difference there, right? Why is there such a difference in the ions or the lattice energy? Well, there's two things. First of all, we've got a larger charge on the magnesium compared to the sodium. So we're doubling the charge. We should expect a doubling of the electrostatic potential as well. And so that accounts for part of it. The other thing that accounts is, again, our periodic trend of size. Magnesium and sodium are in the same row. Magnesium's got more effective nuclear charge. It's a little bit smaller. So it actually has two things going for it. It's smaller and it's more charged. As a result, it has a larger lattice energy. So lattice energy governs a lot of the energetics that we see for ionic compounds. And again, this goes in the opposite direction as well. If I want to break the crystal, if I want to smash it back into its ions, that's how much energy it's going to take to do so. All right, let's talk about covalent bonding. Covalent bonding operates on a similar kind of idea. But instead of a transfer of electrons, we are looking at a sharing of electrons. Now, that sharing of electrons does have some distance considerations to it as well. Atoms that are far apart from each other aren't going to be able to share electrons because they're not close enough each other. This atom can't feel the electrons of this one, and vice versa. So there is a point where those atoms can get close enough together where not only do they feel each other's nuclei, feel each other's electrons, but that attraction is actually at a sweet spot. We call that a energy minimum. That distance is what we would call the bond length for that bond. And the energy that it takes to get there is the bond energy. Now, you may be thinking, well, okay, why this distance? Why not a little bit closer? After all, if they get close enough to each other, their attractive forces are going to increase, right? And the answer is yes. You're right. Attraction does increase as we get closer and closer together. The difference here is that we are not talking just about a positive and a negative attracting each other. Because these are atoms, full-on atoms, and uncharged, we have to worry about repulsion forces as well. The closer those two atoms get to each other, the closer their nuclei are going to get to each other. And if we get them too close, the nuclei actually would start to repel each other and push them back out. So that's why we can see that this minimum here is not as close as the atoms can be to each other. It's actually a little bit further apart than that. We have to do two things: maximize attraction while minimizing repulsion. That's the difference between covalent and ionic bonding. Ionic bonding, because I've got a positive and a negative, they're going to attract each other regardless of how close they are to each other. The only limiting factor is the size of the atoms themselves. But because I have two uncharged atoms here, I have to account for their mutual attraction, but also their mutual repulsion. If I get them too close, that mutual repulsion actually is too big. It's going to take up too much. Already talked about metallic bonds, so we'll just leave that one be. Let's keep going with covalent. In these shared electrons, in these bonds made up of shared electrons, that sharing that occurs is not always going to be an equal sharing. Some atoms are going to be better inclined, more inclined to attract electrons than others. And so what we have here are three different scenarios. The first scenario is even sharing. Where do we see even sharing? Usually between two atoms of the same kind. So if a chlorine atom bonds to another chlorine atom, those two chlorine atoms are going to share those electrons evenly. And it's not really going to be a competition because each one of those chlorines has an equal amount of attraction to the electrons as the other one does. We also could have uneven sharing. That's what this middle one is. In the middle, we can see that the chlorine has a greater level of attraction to the electrons than the hydrogen does. And as a result, it pulls some of those electrons in that bond just a little bit toward itself. We end up getting a covalent bond. They are still sharing electrons here, but it's an uneven sharing. Those electrons are going to spend just a little bit more time with the chlorine than with the hydrogen. But they're still attracted enough to the hydrogen that they're going to hang out over at Uncle Hydrogen's house occasionally too. That is a difference between the polar covalent and this last one. That last one there is an ionic bond. In an ionic bond, that chlorine has such an affinity for that electron that it just flat out takes it. And we can see on this color temperature map, the area around the sodium, cold. That electron's not there. That area around the chlorine, hot. That electron is always there. So there's no evenness in sharing. There's not even unevenness in sharing. It's just flat out theft. Now, how do we know what kind of bond we're going to ultimately end up seeing? How even the sharing is going to be? That's where this concept of electronegativity comes in. Electronegativity can explain the idea of bond polarity by giving us basically a ranking system that says okay, these atoms have the greatest affinity, the greatest attraction to electrons. And these other ones have a lesser attraction. And depending upon how different the two atoms are in terms of their electronegativity, that can give us an idea of what kind of bond it would make. So obviously, if I have two atoms of the same kind, the difference in their electronegativities is going to be 0. That difference of 0 indicates a nonpolar bond. In fact, anything up to about 0.4 or so in terms of difference is a pretty good guideline for determining that's nonpolar. If it's polar, it's only slightly polar. In our example, we had hydrogen chloride. Difference between hydrogen 2.1 and chlorine 3.0 is 0.9. That is right in the middle of the polar range. Polar range is anything up to about 2. Once we hit that difference of electronegativity of 2 or greater, that's when we can start to think of things as being more ionic-like. So sodium chloride, difference there, 3.0 minus 0.9, that's 2.1. One thing that we do need to understand about this is that these definitions, this is kind of a continuum. There's some fluidity in these definitions. They're not hard and fast rules, but they give us some general guidelines, some general guidance as to what kind of bonding to expect. And to be really, really honest, this line between polar and ionic, that one's the most blurry. Because in there, you're going to find compounds that we would traditionally think of as ionic. We would name them like ionic compounds. But if we look down at their crystalline structures, if we look at what they actually look like in their three-dimensional bonding space, they kind of look covalent. Aluminum chloride is a great example of it. Aluminum chloride, we think of as an ionic compound. Al3 plus, 3 chloride minuses. It has a little bit of covalent character if you actually examine its X-ray crystallography. So there's some blurriness there. So don't get too caught up on the labels. Just understand that there are even and uneven sharing kinds of principles that are at play here.